Welcome! In this session, we'll dive into solving LeetCode problem number 2055, plates between candles. This problem challenges us to efficiently calculate the number of plates between specific candle positions across multiple query ranges. We'll explore a structured approach to solve it step by step. Let's get started. In this problem, you are given a string S that consists of two types of characters, the pipe symbol, which we will refer to as candles, and asterisks asterisk, which represent plates. Additionally, you are provided with a 2D array called queries. Each query specifies a range within the string using two indices, left underscore I and right underscore I. The goal is to determine, for each query, how many plates are situated between the leftmost and rightmost candles within the specified range. If there are no candles in the given range, the result for that query will simply be 0. Finally, you are required to return an array where each element corresponds to the result for a specific query. The problem constraints ensure that the string length n can be up to 100,000, and the number of queries m can also go up to 100,000, so efficiency is a key consideration here. Let's look at an example to better understand the task. Suppose the input string is s equals asterisk 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 asterisk, and the query array is queries equals 2, 5, 5, 9. For the first query, the range specified is 2, 5, corresponding to the substring asterisk asterisk. Within this range, there are two plates situated between the leftmost candle at index 2 and the rightmost candle at index 5. Hence, the answer for the first query is 2. For the second query, the range 5, 9 gives the substring asterisk asterisk asterisk. Here, there are three plates between the leftmost candle at index 5 and the rightmost candle at index 9. Thus, the output for this query is 3. Combining these results, the output for this input is 2, 3. Now, let's examine a second example. Here, the input string is s equals asterisk 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 asterisk, and the query array is queries equals 1, 17, 4, 5, 14, 17, 0, 20. For the first query, 1, 17, the substring is asterisk 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 asterisk. In this range, there are 9 plates between the leftmost candle at index 3 and the rightmost candle at index 16. For the second query, 4, 5, the substring is asterisk. Since there are no plates between the candles, the result is 0. For the third query, 14, 17, the substring is asterisk 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 asterisk. Again, there are no plates between candles, so the result is 0. Finally, for the fourth query, 0, 20, the substring is asterisk 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 asterisk. Here, there are 11 plates between the leftmost candle at index 3 and the rightmost candle at index 18. Combining these results, the output for this example is 9, 0, 0, 11. The problem also comes with several constraints and edge cases to consider. The string length n and the number of queries m can both be as large as 100,000, so it is critical to design an efficient solution. For edge cases, if the string contains no candles, meaning it is composed entirely of plates, all queries will result in 0 since there are no candles to enclose the plates. Similarly, if the string contains only candles, all queries will also result in 0 because there are no plates. For very short strings, like when n equals 1, any query will always result in 0 as well, since a single character cannot form a valid range with plates between candles. Finally, overlapping query ranges must be handled carefully, and pre-computation techniques can be used to improve efficiency and avoid repetitive calculations for overlapping segments of the string. To solve the problem of finding plates between candles efficiently, we need to handle potentially large input sizes and multiple queries without redundant computations. The first approach we considered is the brute force method. Here, for each query, we examine the substring defined by the query range, identify the positions of the first and last candles in that range, and count the plates between them. While the intuition behind this method is simple, it becomes inefficient for large inputs. The time complexity is O(m*n), where m is the number of queries and n is the length of the string, because we reprocess the string for every query. This makes it impractical when both the string length and the number of queries are large.
To address this, we explored an optimized approach that uses pre-processing to reduce the query time dramatically.
By leveraging prefix sums and additional helper arrays, we can process the string once and answer each query in constant time. The optimized approach revolves around pre-processing to make query evaluation efficient. First, we create a prefix sum array called plates_count, where each entry at index I stores the cumulative count of plates up to that position. Additionally, we create two helper arrays, nearest_left_candle and nearest_right_candle, which store the indices of the closest candles to the left and right of each position in the string, respectively.
These arrays allow us to quickly find the boundaries of valid ranges for any query. Once pre-processing is complete, we can evaluate each query efficiently. For a given range, we use nearest_right_candle to locate the first valid candle within the range and nearest_left_candle to find the last valid candle.
If candles are found, we calculate the number of plates between them using the prefix sum array by subtracting the cumulative counts at the two boundaries.
If no valid candles exist, the result is simply 0. This approach reduces the pre-processing time to O(n), the query time to O(1) for each query, and the space complexity is O(n). The key advantage of this approach is that prefix sums and helper arrays allow for extremely fast calculations during query evaluation. Another possible optimization is to use binary search on a pre-computed list of candle indices. In this method, we first create an array candle_indices, which stores the positions of all candles in the string. For each query, we use binary search, specifically the bisect_left and bisect_right functions, to find the first and last candle indices that fall within the query range. Once these indices are identified, we can calculate the number of plates between them using the prefix sum array. This approach has a pre-processing time of O(n) and a query time of O(m*log n), which is slightly slower than using the nearest candle arrays because of the cost of binary search. While this method avoids the need for additional arrays like nearest_left_candle and nearest_right_candle, it introduces the overhead of searching within the candle indices for each query. As a result, while it may be cleaner in some implementations, it is generally less efficient for handling high volumes of queries. After evaluating the different approaches, we selected the optimized approach that uses prefix sums and nearest candle arrays as our primary solution. This method is highly efficient, as it processes the string in O(n) time and answers each query in O(1) time, making it well suited for large inputs with many queries. The simplicity of this approach also makes it easier to implement, as prefix sums and nearest candle arrays provide an intuitive way to calculate results without additional complexity. Furthermore, it scales effectively under maximum constraints, such as when both the string length and the number of queries reach their upper limits of 10 to the power of 5. Although the binary search alternative is viable and avoids the need for extra arrays, its slightly higher query time of O(log n) makes it less optimal for scenarios with a high number of queries. On the other hand, the brute force approach, while straightforward, is prohibitively slow for large input sizes due to its O(m*n) time complexity. Thus, the prefix sum-based solution strikes the best balance between efficiency, simplicity, and scalability. The problem plates between candles challenges us to efficiently count the number of plates, represented by asterisks, that are located between two candles, represented by vertical bars, for a series of queries within a string. A query specifies two indices, and we need to determine the count of plates between the nearest candles within that range. The difficulty lies in efficiently handling large input sizes and multiple queries. To achieve this, we use a combination of prefix sums and pre-computed indices. The first step is to pre-compute the indices of the nearest candles. For this, we construct two arrays. The first, left_candle, keeps track of the index of the nearest candle to the left of or at any given position. The second, right_candle, does the same but for the nearest candle to the right. Initially, left_candle is set to -1, implying no candle exists to the left of a position. We then iterate through the string from left to right, updating this array whenever we encounter a candle. Similarly, for right_candle, we initialize it with the length of the string, indicating no candle exists to the right initially, and update it while traversing the string from right to left. These arrays allow us to define the boundaries for valid plate counting in constant time during query processing.
Once we have the nearest candle indices, the next step is to compute a prefix sum array for the plates. This array, called plates_prefix, stores the cumulative count of plates from the start of the string up to each index. With this data structure, we can quickly determine the number of plates within any range using the formula plates_prefix, or plates_prefix, L1. After constructing the prefix sum, we move on to processing the queries. For each query, we use the right_candle and left_candle arrays to find the nearest candles that define the valid range for plate counting. Specifically, we determine the index of the nearest candle to the right of the left query boundary, L, and the nearest candle to the left of the right query boundary, R. If the starting candle index exceeds the ending candle index, it means no valid plates exist between the candles, and the result for that query is 0. Otherwise, we calculate the number of plates between these boundaries using the prefix sum. This approach ensures that each query result is obtained in constant time. Finally, we return the results of all the queries as an array. The key insight here is that the pre-computed arrays and prefix sum significantly optimize the solution by reducing the time complexity of each query to constant time. This efficiency is achieved by leveraging pre-computation, which shifts the bulk of the computational effort to the pre-processing phase. This allows us to handle multiple queries efficiently. Additionally, the use of the prefix sum enables rapid range queries, making it an ideal choice for this problem. The data structures used include the left_candle and right_candle arrays, which store the nearest candle indices, and the plates_prefix array, which maintains cumulative plate counts. Intermediate variables like start and end are used to define the valid range for plate counting during query processing. Together, these structures ensure that the space complexity remains linear, proportional to the length of the string. In terms of complexity, the pre-processing step involves constructing the left_candle, right_candle, and plates_prefix arrays, all of which require linear time, or O(n), where n is the length of the string. Each query is then processed in constant time, or O(1), due to the pre-computed data. Combining these, the overall time complexity of the solution is O(n) plus q, where q is the number of queries. The space complexity is O(n), as the pre-computed arrays require storage proportional to the length of the string. It's also important to consider edge cases. These include scenarios such as queries where there are no candles in the specified range, resulting in start being greater than end, strings with no plates or no candles, and cases where candles are adjacent, leaving no space for plates between them. Proper handling of these edge cases ensures the robustness of the solution. To illustrate the algorithm, consider the string ******** and the queries 1, 5, 0, 6, 3, 7. The pre-computed arrays would be as follows: left_candle stores 0, 0, 0, 3, 3, 5, 5, 7, indicating the nearest candle to the left of each index. Similarly, right_candle stores 0, 3, 3, 3, 5, 5, 7, 7, representing the nearest candle to the right of each index. The plates_prefix array is 0, 0, 1, 2, 2, 3, 3, 4, which holds the cumulative count of plates up to each position. Now, for the first query 1, 5, the nearest candles are at indices 3 and 5. The number of plates between them is calculated as plates_prefix 5, plates_prefix 3 to 1 equals 3, 1 equals 2. For the second query 0, 6, the nearest candles are at indices 0 and 5, and the plates between them total 3. Finally, 4, 3, 7, the nearest candles are at indices 3 and 7, resulting in 3 plates. The output for all queries is 2, 3, 3. Here, we begin the implementation by defining our plates between candles function inside the solution class. The input parameters are a string s, representing the arrangement of plates and candles, and a list of queries, where each query specifies a range within the string. First, we calculate the length of the string and initialize 3 arrays, prefix_sum, left_candle, and right_candle. These will help us efficiently compute the number of plates between candles for any given range. The prefix_sum array will store the cumulative count of plates, up to each index, while left_candle and right_candle will track the positions of the nearest candles to the left and right of each index, respectively. Next, we populate the prefix_sum array. We iterate through the string, and for every plate we encounter, we increment the cumulative count. This allows us to efficiently retrieve the number of plates within any subrange later. After that, we construct the left_candle array by iterating through the string again. We maintain a variable left to store the position of the last candle we encountered as we traverse. If the current character is a candle, we update the left variable. For every index, we store the position of the nearest candle to the left, or -1 if there is none. Similarly, we populate the right_candle array, but this time, we traverse the string in reverse. We use a right variable to store the position of the last candle encountered during the backward iteration. For every index, we record the nearest candle to the right, or -1 if there isn't one. These pre-computed arrays will allow us to answer each query in constant time. Now, we process the queries using the pre-computed arrays. We initialize an empty list called result to store the answer for each query. For each query, which specifies a range, L, R, we use the right_candle array to find the nearest candle to the left of or at index L, and the left_candle array to find the nearest candle to the right of or at index R. These values, left_bound and right_bound, represent the boundaries of the valid segment of the range that contains candles. If valid bounds exist, meaning both left_bound and right_bound are not -1 and left_bound is less than right_bound, we calculate the number of plates between these bounds using the prefix _sum array. Specifically, we subtract the cumulative count of plates at left_bound from the cumulative count at right_bound. This difference gives us the number of plates between the two candles. If the bounds are invalid, meaning no candles enclose the range, we append 0 to the result list. Once all queries are processed, we return the result list, which contains the answers to each query. This approach ensures that we efficiently handle the problem, leveraging pre-computation to answer each query in constant time. Here we start by importing the necessary classes from Java's utility package and defining the solution class along with the plates between candles method. The input consists of a string S, which represents a row of plates and candles, and a 2D array queries, where each query specifies a range of indices. The goal is to calculate the number of plates between the closest pair of candles in the specified range for each query. To efficiently solve this, we first initialize 3 arrays, prefix sum, left candle, and right candle. The prefix sum array will store a running total of plates encountered up to each index. We calculate this by iterating through the string and incrementing a count variable whenever a plate, represented by asterisk, is encountered. This count is then stored in the prefix sum array for the corresponding index. Additionally, we construct the left candle array, which tracks the nearest candle to the left of each position. Using a variable left initialized to -1, we update the position whenever we encounter a candle, represented by, and assign this value to the left candle array for each index. Next, we construct the right candle array, which serves a complementary purpose to left candle by tracking the nearest candle to the right of each position. Here, we iterate from the end of the string toward the start, using a variable right initialized to -1. Whenever a candle is encountered, its position is stored, and this value is assigned to the right candle array for the current index. With these arrays prepared, we can now process the queries. For each query, we extract the left and right bounds from the queries array and locate the nearest candles within this range using right candle for the left bound and left candle for the right bound. If valid bounds exist, meaning both candles are found and the left bound is less than the right bound, the number of plates between these candles is calculated using the prefix sum array. Specifically, the difference in cumulative plates between the right and left candle positions gives the desired result. If the bounds are not valid, the result for that query is simply set to 0. Finally, after processing all the queries, the result array holding the answers is returned. This array contains the number of plates between the closest pair of candles for each query. The approach is efficient because the pre-processing steps of constructing the prefix sum, left candle, and right candle arrays ensure that each query can be resolved in constant time. This makes the solution well suited for handling large inputs, as the overall complexity is linear with respect to the size of the string and the number of queries. Here, we're introduced to the problem using the string s equals ******** and the queries 1, 5, 1, 6. The goal is to determine the number of plates, or asterisk characters, between two candles, represented by, for each query. To solve this, we first pre-compute a prefix_sum array to track the cumulative count of plates up to each index. Starting with an initialized array of zeros, we traverse the string character by character. For positions with a plate, we increment our running count and store it in the prefix_sum array. For positions with a candle, the count remains unchanged. By the end of this traversal, the prefix_sum array gives us a quick way to determine the number of plates in any range with just a subtraction. For this example, the resulting array is 0, 1, 2, 2, 3, 3, 4, where each value corresponds to the cumulative count of plates up to that index in the string. Next, we calculate the nearest candles to each index, both from the left and the right. First, we compute the left_candle array by scanning the string from left to right. This array tells us the index of the closest candle to the left of each position. Whenever we encounter a candle, we update our left pointer to that index, and for all other positions, we use the last seen candle's index. For this example, the left_candle array becomes 0, 0, 0, 3, 3, 5, 5. Similarly, we compute the right_candle array by scanning the string from right to left. This array tells us the nearest candle to the right of each position. For positions without a candle, we use the most recently seen candle's index. If no candle exists to the right, we assign -1. The resulting right_candle array is 0, 3, 3, 3, 5, 5, -1. These two arrays now allow us to quickly determine the bounds of valid ranges for each query. With our pre-computations complete, we can now efficiently process the queries. For the first query, 1, 5, we use the right_candle array to find the nearest candle to the right of index 1, which is at 3. Similarly, we use the left_candle array to find the nearest candle to the left of index 5, which is also at 5. With these bounds, we calculate the number of plates between these candles using the prefix_sum array, prefix_sum, 5, prefix_sum, 3, equals 3, 2 equals 1. For the second query, 1, 6, the nearest right candle for index 1 is again at 3, and the nearest left candle for index 6 is at 5. Using the same calculation, the number of plates is again prefix_sum, 5, prefix_sum, 3, equals 1. The final output for both queries is 1, 1. In this example, we examine a case where no plates exist between candles in some queries. The string is s equals asterisk asterisk, and the queries are 0, 4, 2, 4. After pre-computing, we have prefix_sum equals 0, 1, 1, 2, 2, left_candle equals 0, 0, 2, 2, 4, and right_candle equals 0, 2, 2, 4, 4. For the first query, 0, 4, the nearest right candle to index 0 is itself at 0, and the nearest left candle to index 4 is at 4. The plates between these bounds are prefix_sum, 4, prefix_sum, 0, equals 2, 0 equals 2. For the second query, 2, 4, the nearest right candle to index 2 is at 2, and the nearest left candle to index 4 is at 4. The plates between these bounds are prefix_sum, 4, prefix_sum, 2, equals 2, 1 equals 1. The final output is 2, 1. Finally, we consider an edge case where the string contains only one candle, s equals, and the query is 0, 0. After pre-computations, we have prefix_sum equals 0, left_candle equals 0, and right_candle equals 0. For the query, the nearest right candle to index 0 is at 0, and the nearest left candle to index 0 is also at 0. However, since the bounds do not enclose any plates, the result for this query is 0. The final output is 0, demonstrating how the solution handles scenarios with no valid plates between candles. To analyze the time complexity of our solution, we break it down into three main pre-processing steps and the query evaluation loop. First, we have the construction of the prefix_sum array. This array keeps track of the cumulative count of plates, represented by asterisk, up to each index in the string s. Since we only need one traversal of the string of length n to compute this, the time complexity of this step is O(n). Next, we have the left_candle array, which stores the nearest candle, represented by, to the left of each index, or at the current position. This also requires just one traversal of the string, so its time complexity is O, n. Similarly, the right_candle array is built to store the nearest candle to the right of each index. This step involves a single reverse traversal of the string, making its time complexity O, n, as well. Now, for query evaluation, each query, L, R, involves determining the nearest candles at the boundaries using the right_candle and left_candle arrays. Once these boundaries are identified, the number of plates between the candles is computed using the prefix_sum array. Since all these operations are constant time, or O1, the time complexity for a single query is O1. If there are Q queries in total, the query evaluation step becomes O(Q). Combining the pre-processing steps, which are O, n, with the query evaluations, which are O, Q, the overall time complexity of the solution is O, n plus Q. Let's now evaluate the space complexity of the solution. First, we consider the input storage. The string S has a length of n, and the query's array contains Q elements, so the input storage requires O, n plus Q, space. Next, we have the auxiliary arrays. The prefix_sum array, used to store cumulative plate counts, has a length of n, so it requires O, n, space. Similarly, the left_candle and right_candle arrays, which store the nearest left and right candles respectively, each have a length of n, contributing O, n, space each. Finally, the output storage, which holds the results of the Q queries, adds an additional O, Q, space. When we sum these components, the total space complexity of the solution is O, n plus Q. In contrast to the optimized solution, the naive approach involves scanning the substring L, R for every query to count the plates between candles. For Q queries, this leads to a time complexity of O, Q asterisk K, where K is the average length of the substring being scanned. In the worst case, K could be as large as n, resulting in a time complexity of O, Q asterisk n. The optimized solution significantly improves upon this by pre-processing the string in O, n, and answering each query in O, 1, yielding a total time complexity of O, n plus Q. When analyzing specific scenarios, the best case occurs when the string contains only candles, meaning no plates are counted. Even so, the pre-processing and query evaluation still require O, n plus Q. In the average case, for a typical string with a mix of plates and candles, the time complexity remains O, n plus Q. In the worst-case scenario, the string is very long, and there are many queries. While the pre-processing steps may dominate, the total time complexity still remains O, n plus Q. To confirm this formally, we can break it down mathematically. The pre-processing involves 3 linear traversals of the string, each taking O, n, resulting in a total pre-processing time of O, n. Query evaluation involves constant time operations, such as array lookups and basic arithmetic, for each query, leading to a total query time of O, Q. Combining these, the overall time complexity is O, n plus Q. Regarding space usage, the auxiliary arrays, including prefix_sum, left_candle, and right_candle, dominate, along with the result array for the queries. This gives a total space complexity of O, n plus Q. Compared to the naive approach, this optimized solution is significantly more efficient, especially for larger values of n and q. When tackling this problem, there are a few common mistakes that can trip people up. First, using a brute force implementation to handle multiple queries is a major pitfall. This approach involves iterating through the string for every query, leading to a time complexity of O, n asterisk q. For large inputs, this is far from efficient. Instead, you should use pre-processing techniques like prefix sums and binary search to bring the query time down to O(1) or O log n. Another mistake is forgetting to handle edge cases where there are no candles in the substring. This can lead to index errors or completely incorrect results. To avoid this, always verify that there's at least one candle in the queried range before attempting to calculate the number of plates. Additionally, misinterpreting how to use prefix sums can cause frustrating off-by-one errors. This typically happens when the indices of candles aren't properly aligned with the indices of the prefix sum array. Careful alignment during pre-processing is key to avoiding these issues. Finally, inefficiently searching for the closest left and right candles by scanning the string linearly for each query wastes time. A better approach is to pre-compute the nearest left and right candle indices for every position in the string, allowing for O1 lookups during queries. Now, let's consider another common issue: not handling large input sizes effectively. When the string becomes very large or there are a high number of queries, a poorly optimized solution can easily exceed time limits. To mitigate this, make sure to test your implementation with edge cases that simulate these scenarios, confirming that both pre-processing and query handling are scalable. Shifting to interview insights, this problem is an excellent example of pattern recognition.
It combines prefix sums with range query optimization, concepts that are foundational for many interval-based problems. Interviewers will often expect you to identify the inefficiencies of brute force approaches and demonstrate how to transition to pre-processing techniques like prefix sums or binary search. It's also important to discuss edge cases during your explanation, situations such as no candles in the range, the entire range being surrounded by candles, or overlapping queries. Lastly, emphasize scalability. Highlight how pre-processing minimizes query time, making the solution efficient even for very large inputs. This demonstrates your ability to handle both correctness and performance considerations effectively. To deepen your understanding of this problem, it's helpful to explore related problems that involve similar techniques. For instance, LeetCode 303, range sum query, immutable, similarly relies on prefix sum pre-processing for efficient range queries. Another example is LeetCode 1094, carpooling, which deals with interval handling and uses prefix sums to optimize computations. Then there's LeetCode 238, product of array except self, which also demonstrates a prefix sum-like approach, though in this case, it's applied to products rather than sums. Finally, LeetCode 715, range module, is a more advanced problem that involves range query and interval management. By working on these problems, you'll not only reinforce the techniques covered here but also gain exposure to a broader set of use cases for prefix sums and interval handling, which are extremely valuable in competitive programming and technical interviews alike. There are also alternative approaches to solving this problem, each with its own trade-offs. A brute force approach involves iterating through the substring for each query to count the plates. While this method is simple to implement, it's highly inefficient for large inputs due to its O(n*q) time complexity. A more efficient option is to pre-compute the indices of all candles and use binary search to find the closest left and right candles for a query. This reduces query time to O log n, making it faster than brute force, though not the most optimal. The best approach combines prefix sums with pre-computed nearest candle indices. With this method, you pre-process the plate counts using a prefix sum array while also preparing arrays for the nearest left and right candles for each index. This allows for O1 query time after an O(n) pre-processing step. While this solution is optimal in both time and space, it does require additional storage for the pre-computed arrays. Each of these methods has its merits, but understanding their trade-offs is key to selecting the right approach based on the constraints and requirements of the problem. Great job! To recap, we tackled the plates between candles problem using an optimized approach involving prefix sums and pre-processing. This method is especially useful for scenarios with multiple queries, offering a balance of efficiency and clarity. Don't forget to practice similar problems to reinforce your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!